OmniTouch is a wearable system that enables graphical, interactive, multi-touch finger input on everyday surfaces. Our system allows wearers to interact with applications on their hands, arms, legs, books, walls, tables, and many other surfaces. Importantly, these interactions can proceed on the go, with no calibration, training, or instrumentation of the environment or the user beyond our shoulder-worn system. Our finger tracking approach can localize multiple fingers in 3D space and determine if they are hovering above or clicked on a surface. Our system also identifies, tracks, and classifies surfaces suitable for projected interfaces. The primary components are a short-range depth camera and a pico projector. Please refer to the paper for details. To evaluate the performance of our system, we conducted a user study. Participants completed crosshair clicking trials on the hand, arm, pad, and wall. To investigate dragging performance, participants also completed a series of drawing tasks. The results suggest our prototype system approaches the accuracy of conventional, physical touchscreens, but on arbitrary, ad hoc surfaces. To showcase our system's capability, we developed numerous demonstration applications. In this example sequence, a user is alerted to a new email. They are prompted to open the message, and then select an area for viewing. Rather than viewing the message on the small confines of the hand, the user instead approaches a nearby wall and defines a region for the email to appear. Here, a user clicks their palm to summon an application launcher, selects the phone app, and dials a number. We explored several methods for defining the position and size of interfaces. In some cases, it is easiest and often best to let users define where applications should appear. However, in other cases, it is possible for OmniTouch to make a reasonable approximation automatically. We also implemented a variety of conventional interactions, including hierarchical list navigation with scrolling, map panning and zooming, a full QWERTY keyboard, and digital post-it notes. Here, a user demonstrates painting on their hand. The same application could also be used to annotate a document they are reviewing. If multiple surfaces are present in the system's field of view, applications could intelligently distribute functionality. For example, here a user is painting on a wall. The left hand could be raised to provide a palette of colors. Also, when a user is seated, applications could be projected onto the tabletop. The hand could serve as a transient application toggle. Finally, depth cameras provide a variety of metadata that applications could use to be more powerful and context-sensitive. For example, the distribution of surface normals can be used to infer if a surface is public or private. OmniTouch uses a depth camera-driven, template matching and clustering approach for multi-touch finger tracking on everyday surfaces, including walls, doors, tables, notepads, books, and even one's own body. First, we take a depth map of a scene and cull values that lie outside of one arm's length. This isolates the arms, objects we might be holding, or large surfaces we are standing near, such as walls. We then compute the depth derivative in the x and y axes using a sliding 5x5 pixel window. We then iterate over this derivative image, looking for vertical slices of cylinder-like objects. This is similar to template matching, but with some simple dynamic parameters. Put simply, for a column of pixels to be a candidate finger slice, it must show a steep positive derivative, followed by a region of relative smoothness, and finally closed by a steep negative derivative. To isolate fingers, candidate slices must be between 5 and 25 millimeters in length. All other slices are discarded. Once all candidate finger slices are identified, we then greedily merge proximate slices into contiguous paths, shown here in red. Paths that are shorter or longer than probable fingers, again in real-world units, are discarded. As can be seen, the output resembles a skeletal model of the fingers. Like other computer vision techniques, fingers that are occluded are not detected. Usefully, this means fingers that are tucked in are not tracked for input. To detect clicking, we do a bounded flood fill operation starting at the fingertip, using a depth delta tolerance of roughly 1 centimeter. Typically, the flood fill expands to encompass the finger. However, when a finger is touching an object, the fill operation floods out onto the contacting surface as well. We detect this as a finger click.